Okay, so far in our transmission line lecture videos, we have considered the case where we have a single transmission line connecting a generator, which we're modeling as a DC voltage or a battery with a source resistance, to a transmission line. And at the other end of that transmission line is a load, which we're characterizing with a resistor. So in the next few lectures, we're going to remove a few restrictions on this. The first in this lecture is we're going to talk about what happens if we have multiple transmission lines connected together. And we're going to call that either cascaded or fan-out lines. In the lecture after that, we're going to consider what happens when we turn off a battery or when we disconnect a source and what happens in that case. So basically, we're considering the turn off or the down flipping of a digital circuit. And then we're going to consider what happens when we have loads that are not resistors, but potentially capacitors and inductors. So those will be the upcoming material, but we're going to start in this lecture by removing the one transmission line only restriction. We'll talk about cascaded and fanned out lines. So this lecture is divided up into three sections. The first is called cascaded transmission lines. That is the case where you have a transmission line connected directly to another transmission line. In the second section, we'll be talking about what's called parallel fan-out. Parallel fan-out is when a single transmission line splits into two transmission lines that are connected in parallel to the original. And series fan-out is when a transmission line splits in two, but the other two are connected in series, not in parallel. So we'll cover these in order. First, cascaded transmission lines. All right, so let me draw what this will look like. Going back to the traditional circuit diagram here, we've got a battery here. Hang on a second. We've got a battery connected to a generator resistance, which we're calling RG. The value of the voltage is VG. And we then have a switch right here that's going to close at t equals 0. I haven't always drawn this switch in, but it's been there because at the moment we're only considering the turn on. So we're always considering that, that turning on at t equals 0. And then when that happens, we're going to connect to this system where we've got one transmission line noted with these two pipes. This transmission line has an impedance Z0. And at the end of this transmission line, we have to this point been drawing a resistor, and we're calling that the load. But what we now want to consider is what if one transmission line simply connects to another transmission line, like this. And this second transmission line can have a different impedance to it than the original one. We'll call that intrinsic impedance Z1. Right, and with the assumption that it's different from that of Z0. As an example of this, consider a transmission line that would be a single trace on a circuit board over the top of a ground plane. Right, so this could be a circuit board, you've got a trace in a ground plane, but say at a certain point the ground plane ends, right, and you only have a ground trace on the other side, and then that continues on. That would be a transmission line switching into a different kind of transmission line that has a different impedance at the junction. So that's an example of what could lead us to a situation like this. And that, again, could potentially be very common in a circuit board or in an integrated circuit, anytime the conditions of the transmission line change along a path or along a trace. Okay. Now, so far, we've been considering a reflection that occurs at this load. And we also know that there's going to be a reflection here at the source. I'm going to call this gamma G. That is the voltage reflection coefficient at the generator side. And we've been defining this gamma, this reflection coefficient, at the load side. Now, in this case, we have to be a little bit more careful because the load is no longer where it was before. Right now, we've got the load resistor over here. We'll call that RL. And our reflection coefficient over here, we're going to call that gamma L. But we're also going to see that there are reflections that could occur at this junction. And it could happen in two directions. It could be a reflection of a wave that's on line 0 and encounters the line 1, or could be coming along line 1 encountering the junction with 0. So I'm going to denote these with the symbol gamma 0, 1, which is the reflection coefficient for a wave from Z0 hitting the junction with Z1 and turning around and going backwards. On the other hand, we're going to have gamma 1, 0, which will denote the reflection coefficient for a wave coming from the load back toward the reflection and then toward the junction, and it turns around and goes backwards toward RL. Okay, so when we first turn on the circuit, when we close that switch, everything is going to look the same as it would before. We're going to inject a V in, and V in will be our generator voltage, and we're going to apply a resistor divider or an impedance divider with Z0 and RG. So this will be times Z0 divided by RG plus Z0. And so we're just dividing up that voltage between the generator resistance and between the transmission line. So that's not going to change. All right. What is going to change is what happens thereafter, because now we have an extra junction to take care of and to handle the transmissions. All right. So I'm going to draw here a bounce diagram, and there's going to be 3 lines in this bounce diagram to denote the first part of the transmission line and the second part of the transmission line. And let's draw this V in right here, reaching this junction. So here's a V in proceeding this way. All right. Now, we've got this reflection coefficient gamma 0, 1, which we can define gamma 0, 1. The way we're going to define that is we're going to treat Z1 as if it were a load resistor, right? So the new transmission line impedance acts just like it were a resistor in terms of creating reflection. So gamma 0, 1 will be Z1 minus Z0 divided by Z1 plus Z0, right? It's the same equation that we used before for the reflection coefficient, except the only difference is instead of a load resistor, we're swapping in Z1. We can also define gamma 1, 0, which is the same, except we're swapping what is the line and what is the load. And so Z1 and Z0 basically are swapped with each other. Z0 minus Z1 over Z1 plus Z0. From this, you can probably see right away that gamma 0, 1 equals negative gamma 1, 0. You have the same reflection coefficient for the waves coming in different direction. They're just multiplied by -1 with respect to each other. Anyways, armed with this knowledge, let's carry this wave on. All right, so we've got this Vn, and this Vn is going to reflect over here. And so the backwards going wave will be Vn times gamma 0, 1, since this Vn wave is propagating along transmission line 0 and striking the boundary with transmission line 1. So that's going to be going this way. Now there's a second piece to this, which is that some of this wave is also going to penetrate into transmission line Z1 and become a new wave. So I'm going to draw this branch over here to indicate the wave that is moving onwards into transmission line 1. And what is the value of that forward propagating wave? Now let's say that prior to this lecture, there's no transmission line here, right? Instead, I had just put RL over here. And I'd ask you the question, what happened to the voltage on RL when this voltage wave comes in? You would have taken the original 0 volts that it started with, and you would have added V into it, and you would have added Vn gamma 0, 1. So the voltage here would have become 0 plus Vn plus Vn times gamma 0, 1. That would have been the voltage on this hypothetical resistor. In this case, it's as if we have a resistor, except its value is Z1. So the second transmission line almost acts as if it were a load, except instead of having the voltage simply jump up on a resistor, that becomes a value of a new wave that is launched into the second transmission line. So let's quantify that and write it down. All right, we're going to go back to this case right here. And so the value of the propagating wave in the second transmission line will be Vn times 1 plus gamma 0, 1. The 1 there represents the incoming Vn, and the gamma 0, 1 represents the reflected wave, both of which build on top of each other and both of which launch a new wave into the second transmission line. Right? From here, you can keep track of everything repeatedly the same way that we did before. So this wave is going to reflect off of the load, and it's going to create a wave that's propagating back in the negative direction. In order to figure out the value of that voltage, we're going to do Vn times 1 plus gamma 0, 1. And we're going to multiply it by another reflection coefficient because it had to bounce off the load. So that will be the value of the voltage that reflects and comes back. This first wave that works its way back toward the source. If the source is not perfectly matched, we're also going to get a reflection over here. And this value will be Vn times gamma 0, 1 times gamma g. Right, that will be the value of the voltage wave that's moving that way. And from here, we can continue this process. When if these two waves were to meet at the same time, we could treat each one separately, calculate what the reflection is and the transmitted wave, and just add up those effects together. Right, these waves are all propagating independently once they kick off and get going. So another way to look at this is we have, for this gamma 0, 1, represents the reflected wave for a wave that comes from Z0 and strikes this boundary. But there's also what we might call a transmission coefficient, tau 0, 1, which is a coefficient that tells us how much waves, what's the voltage wave that's sent into the next transmission line, given what has come in. And tau 0, 1 is going to be equal to 1 plus gamma 0, 1. And this is, again, called a transmission coefficient. So if you prefer, instead of Vn times 1 plus gamma 0, 1, I could write this as Vn times tau 0, 1. It's slightly more compact, but you would get the same answer. And you can repeat this process for the rest of this as well. All right, so, and gamma L, by the way, just to be clear, is the same as we would have defined it before. It's the load resistance minus the impedance of the line that is leading up to that load. So that's Z1 divided by RL plus Z0. Notice that the value of Z0 has nothing to do with the reflection coefficient at the load, because line 0 and the load are physically separated from each other. So the wave never interacts with those two at the same time. It does interact with the load and line 1 at the same time, which is why that is how we determine gamma L. Right. And this process can continue. You may have multiple waves propagating back and forth on both transmission lines until it eventually settles out. All right. I have an example in the notes to take you through with actual numbers and where you can track everything. But just to sort of state one thing right here. So we know how to track what the voltage on the load is. This is going to start out at 0 volts. And then once this wave passes by, it's going to be Vn times tau 0, 1 plus Vn tau 0, 1, which is gamma L. We can also rewrite this as Vn tau 0, 1 times 1 plus gamma L. And if you prefer, you can even replace 1 plus gamma L with tau L. You want to sort of apply the same type of logic where we have like an absorption coefficient that's 1 plus the reflection coefficient, in which case this just becomes Vn times tau 0, 1 times tau L. So that will be the value of the voltage on the load. Right, you can repeat the same process, but let's ask this question. What is the value of the voltage that is at the junction between these two transmission lines? Right, so clearly in this region here, it's going to be 0 volts. But what is it in between? Right, so to do that, we're again just going to follow the same process that we have a Vn plus a Vn gamma 01, that this voltage right here is going to be equal to Vn times 1 plus gamma 01. That will be the voltage in this section. Right? Notice we do not need to add again the third wave that's launched into transmission line 1. That does not get added in because this new wave that's launched is basically a consequence of the reflection. So we would be double counting if we added this as well. So we're going to keep the same structure that we used to figure out if there were a load resistor here that had resistance Z1, this would be the change in voltage on that load resistor. And it's the same process when instead of a load resistor, we have a transmission line with a different impedance. All right, so this is called, again, cascaded transmission lines. And you can follow this process to understand how the waves are going to settle out. And if you follow this far enough along and wait long enough time, we are still going to approach the steady state that we would expect based on basic circuit theory. And that steady state simply is get rid of the transmission lines and just treat this as a simple circuit where you've got VG, RG, and RL. And for a long time in the future, the circuit should precisely reproduce this. The voltage that's on the load will simply be VG resistor divided between RG and RL, and we're going to expect the same amount of current on RL as we would have expected in this case as well. But of course, this is only after a long time do we reach the steady state. So that's cascaded transmission lines. In the next couple of video portions, we're going to talk about transmission lines that split into two, and we'll call that fan-out lines. Before I move on to the next video, I would like to show a simulation or visualization of this cascaded line with this WinTLS software. I can click here on cascaded lines, and I can separately set the transmission line intrinsic impedances of two different lines. So let's set the second transmission line to have 150 ohm resistance. All right, actually, no, let me start out. Let's keep it at 50. And let's do a quick simulation. Again, here's the voltage along the transmission line, and we're simulating forward in time. So here it's moving toward the end. The load is matched. And so once this wave gets to the end, it stops there, and nothing else is going to happen. All right. So now let's change this transmission line here to be 150 ohms. And let's start the simulation again. Okay. Now, as this wave reaches that junction, we expect that there ought to be a reflection at the load. Sorry, at the junction. The reflection coefficient turns out to be 1/2, since it's 150 minus 100 divided by 150 plus 100. So that's a reflection coefficient of 1/2. So we're expecting half of this voltage value to sort of propagate backwards. And what's going to go forwards into the second transmission is the transmission coefficient, which is 1 plus the reflection coefficient. So since the reflection coefficient is 1/2, the transmission coefficient is 1.5. So let's see that in action. All right, so here we go. You can see that reflection has happened. The wave that's now propagating backwards on transmission line 1 has half the value of the wave that came in. These tick marks are 1/2 volt long. So this is a 1/2 volt here, and that's about a 1/4 wavelength is that second wave built on top of it. The wave that's propagating into the second transmission line is the sum of both of those. It's the 1 volt, and it's the 1/2 volt and the 1/4 volt built on top of it. So the transmission coefficient is 1.5 multiplied by the 1/2 volt that's coming in gives us 3/4. So here, let's see this again, and we'll carry the simulation on. I'm going to stop right there. Now we've got two separate waves. One is working its way toward the load. The other is working its way toward the source. On the source side, we have a perfect match between the generator and the transmission line impedance. It doesn't actually happen in real life, but very often, but I'm going to show it in this case just to simplify. On the load side, though, we expect there to be a reflection because the 150 ohms does not match the 50 ohms that's on the load. In fact, we expect a reflection coefficient of -1/2. And so this 3/4 of a volt that's coming in, we're going to expect it to bounce back and have 3/8 of a volt going backwards. So let's step through this and see that happening. All right, remember also the voltage at the source will be absorbed and gone forever. And there's the reflection. All right, so here's the 3/4 coming in, and here's half of that now coming as a negative wave that's wiping out some of that voltage. All right, we can keep this going. I'm going to continue this, in fact, speed it up so you can watch this process play out. Here's the reflection at the junction again. We're going to get some back and forths. If we wait long enough, the entire transmission line is going to settle out. We're going to have the same voltage at all locations along the transmission line. And that voltage will match the steady state value that we expect if we have 1 volt connected to 50 ohms and another 50 ohms, which is half a volt. Again, this tick mark is a half volt, so that is precisely what happened. So you can always do a sanity check, remove the transmission lines and replace them with regular wires, and make sure that your solution is converging toward where it would in that very simple case, that very simple no transmission line case.